शो करना था मुझे, ठीक है ना? Good evening, children. This is Nilesh from Wisdom Academy. I hope you are doing good. So we are on the 4th day of Wisdom Marathon series. So in this series, last 3 days, we have learnt about the first 3 chapters of physics. That is, on the first day, we learnt electric field and charges. On the second day, we learnt electrostatic potential and capacitance. And yesterday's session, we have learnt about current electricity. Today, we are going to go to the 4th chapter, that is magnetism. Basically, I am going to take magnetism and matter and the Earth's magnetism together because the second chapter is a little small. So today we will be covering 4th and 5th chapter together. So if you have not seen the previous videos, please go there and watch that. It has been uploaded in the YouTube. Again, I want to repeat for the people who are new in this video today that we are doing the marathon series, the last minute preparation, what is required for the term 1 board examination, in which we are doing a rigorous revision. It's not like just the formula I am speaking. I am speaking conceptually about each and every topic, and after that we are taking even the MCQ type questions, we are taking assertion reasoning type questions, we are taking passage type questions. So the people who are seeing the video honestly, thoroughly for the entire duration, I can assure you that you will get something from here and go. It will not be a time waste for you. So people who have just studied their portions and want to revise a quick revision for that and to practice some questions, everything is there in this package. So I hope you are making the maximum use of it, and please keep on making use of it. And let us start today's lecture. So before I start, I want to tell to my students to put their attendance because that is very compulsory. You can just send a hi and I'll know that you have come for the class. So people are joining. Yeah, I can see there. So fine. So let us start today's session and let us see what is the first topic of the day. So in magnetism, today we are going to start with the first topic, that is Ørsted's experiment. So before I start talking about Ørsted, I would like to tell you that up to now we have learned the charge which was at rest, and I told you the charge being at rest, if it is stationary, not moving, it will produce an electric field around it, right? So all the charges at rest, whether it is positive charge or negative charge, they produce electric field around it when it is at rest. The same charge, when it starts to move, it is called as current. So what was current? In the last class we have learned, yesterday's session, that current is the rate of flow of charges. If a proton is moving, we say it is a conventional current, that is the direction of current is same as the direction of movement of proton, we call it as conventional current, and the movement of electrons creates electronic current, and electronic current will always have direction opposite to direction of the electrons movement. We found, that is not we, Ørsted found for the first time that the current produces a magnetic field around it. Definitely he found it that is accidentally in his laboratory, where he had a lot of circuits and he had some compasses, and he could see that whenever the circuits were operating, there was some deflection in the galvanometer, in the needle. So when the needle was deflecting, he got an idea that whether this current is producing a magnetic field, and then he did an experiment in which he had some circuit. In the circuit, suppose I am just drawing a basic circuit. He had a circuit like this, and which was carrying current, since it is a closed circuit. When he brought a magnetic needle near to this branch anywhere, so when he brought a magnetic needle like this, he could see that there is some deflection in the needle, which made him to realize, which made him to understand that whenever there is a current flowing through a conductor, there will be a magnetic field coming around it. So magnetic field comes whenever there is a flow of current. Now if you ask me, so what will be the direction of deflection, whether it will go towards west, towards east? So for that, there is a simple shortcut to remember. I call it as snow. Snow is a technique in which you can remember would be the direction of deflection of any compass. So it's very simple. If the current is going from south to north direction, S stands for south, N stands for north, O stands for over, W stands for west. So if the current is flowing from south to north direction and you are placing your magnetic needle over the wire, see, I have two options. If this is the wire, I can place the needle above the wire, that is over the wire, or under the wire. In both the case, it will show different deflection. Remember this. Whenever a magnetic needle is kept over the wire or under the wire, the deflection will be different. So when a magnetic needle was placed over the wire and the current was moving from south direction to north direction, then the needle was deflecting towards west. As simple as it is. So when the current goes from south to north and the needle, magnetic needle is over the wire, the deflection of the north side of the needle will be towards west. I hope you are understanding this. Current going like this and needle kept here. This is the north side of the needle. It will move like this towards the west. That's how needle moves. I am assuming that this needle is over the wire. Same way, if the direction of current is same south to north and you are placing the needle below the wire, or I should say under the wire, if it is placed under the wire, then the deflection of the needle will be towards the east. As simple as it is. And also opposite, if it is going from north to south over the wire, east, north to south, under the wire, west. So don't confuse yourself much, just remember one thing, and all the other things you can easily find. South to north, over the wire, west. In very rare scenario only, you may have a question from here. Generally it won't be asked, but just I told you for the information that we can determine the direction of deflection of the magnetic needle if we know the direction of the current. I hope you have got this. So we'll go to the next page now, where we have the right hand thumb rule. Actually a very important rule, which says that if you stretch your right hand and you point the finger towards the direction of current, then the curled four fingers will give the direction of magnetic field. So suppose I am having a current carrying conductor and I hold, theoretically not really, if I hold the current carrying conductor in such a way that my thumb is giving the direction of current, then my curled four fingers will give the direction of magnetic field. For example, if I have, one second, yeah, so let me assume that there is a wire which is taking current above. So if I hold this wire in my right hand, my fingers are curling like this, right? Something like this. You can see very clearly it is kind of anti-clockwise. So direction of the magnetic field is anti-clockwise. I hope you are understanding. In three-dimensional plane, this is the direction of current, fingers are curling anti-clockwise. If direction of current would have been down, it will turn clockwise. I hope you are getting my point. So direction of current is towards above, then the direction of magnetic field is anti-clockwise. Same way, if the current would have been coming in the downward direction, the direction of the magnetic field would have been clockwise. I hope you are understanding this, that the magnetic field direction is clockwise or anti-clockwise given by right hand thumb rule. It does not end here. Suppose they ask you, they don't want to know overall magnetic field. If they ask you that what is the direction of magnetic field on the point A or towards the right, what would be your answer? See, it's very simple. This is the direction of current. On A, it will point into the plane, and so it is represented by this cross marks. Cross means into the plane. I hope you are understanding this. That, see, put your finger towards the above direction. Your four fingers are trying to go inside the wall, isn't it? Into the plane. So this kind of direction is called as into the plane. Into the plane. And if you see on the left hand side, it will feel as if it is coming out of the plane, and that is represented by this sign, a dot and a circle. This means out of the plane. This kind of representation is done for out of the plane, out of the plane. So, if a current carrying conductor or a current carrying wire is going in the above direction, on the right hand side the magnetic field is into the plane, and on the left hand side magnetic field is out of the plane. Same way, if it is going in the downward direction, you can understand that on this side it will be into the plane, and on this side it will be out of the plane. It completely depends upon which direction the current is moving. Not only top and bottom, even if its current is going like this. You see, my thumb is in this direction. Obviously, this side it will be into the plane, this side out of the plane. I hope you are understanding this. So, this is about the right hand thumb rule, how it helps us to find the direction of magnetic field. So, next comes one of the very important topics of this chapter, that is Bio-Savart Law or Bio-Savart Law, whatever you want to call it, Bio-Savart's Law. So, what did this two people, Bio-Savarts, did, and what did they find? They could find the value or the magnitude of magnetic field for a current element. Now, when I say current element, suppose there is a wire, random wire like this. This wire is having some current flowing in this direction, suppose I, current is going like in this wire. If I take a small portion of the wire, no, this portion is called as current element, current element. So, what is current element? Is the small portion of wire which takes the current. We call it as current element. It is represented by DL, DL. So, this is a small length of the overall length, it is called as DL or current element. So, by Bio-Savart law, you can find what is the magnetic field at any point r distance away from this. So, I want to find from DL, this r distance away, some point is there, let me call it as point P. I want to find what is the magnetic field at P. I can find by using Bio-Savart law. That is the beauty of Bio-Savart law. It will help you in finding the magnetic field at any point near to the wire. I can even take here and find. At this point, suppose it is Q, and suppose this is R2 or something else, R dash, I can find what is the value of magnetic field if I know the Bio-Savart's law. So, let us see what did it tell. I am not going into that much detail today because it is a revision class. What Bio-Savart concluded is that the magnetic field B, I am taking it as dB because for a small element, small magnetic field. If we integrate, I will get the complete magnetic field. So, the small magnetic field dB due to the current element dl is proportional to I, that is more the current, more the magnetic field, less the current, less the magnetic field. It is proportional to dl, that is, if I take a larger current element, I will have more magnetic field. If I take a smaller current element, I will have less magnetic field. Sin theta. Now, theta is the angle made by the current element with the distance r. This is theta. So, sin theta divided by r square, divided by r square. So, from here you can see very clearly that Bio-Savart law said that magnetic field at any point near the wire due to a current element is proportional to current, is proportional to current element, is proportional to sin theta, theta being the angle made by the current element with the distance, and inversely proportional to square of the distance of the point from the wire. I hope I am clear. So, then to remove proportionality, I have to add a constant, and that constant here is k, and that is equal to mu naught by 4 pi, mu naught by 4 pi. Like how in the case of electric field we had 1 by 4 pi epsilon naught, that was called as proportionality constant for the electrostatics. Here we have proportionality constant as mu naught by 4 pi into I dl sin theta by r square. Right. Now, this mu naught is called as permeability of free space, permeability of free space. Epsilon naught was called as permittivity of free space, but mu naught is called as permeability of free space, and for free space the permeability is 4 pi into 10 to the power minus 7. You can put the units, whatever it comes, Tesla, meter square and ampere, whatever it comes. So mu naught by 4 pi, mu naught value is this. So if you put 4 pi into 10 power minus 7 by 4 pi, you will get this whole term as 10 to the power minus 7. So the value of the constant is 10 to the power minus 7. Okay. So this was the basics of Bio-Savart law, which gave you the magnetic field at any point near to a current element. This was the scalar representation of magnetic field. We also have the same thing in vector form. So if I write in vector form, if I want to write what is the value of magnetic field, I write like this. See, dB is equal to mu naught by 4 pi I into dl cross r. Since I have taken r, I will write it as r cube here. You know very well that r cap is equal to r vector by magnitude of r vector, isn't it? So r vector is equal to unit vector into magnitude of unit vector, that is r cap into r. So it will get cancelled anyhow. Don't think it is inversely proportional to cube of r. No, I just written for this r. So this is the vector representation of Bio-Savart law. That is mu naught by 4 pi I dl cross r by r. This question can be asked in the board examination. I can even write like this. I will say one more way of writing. If it wants to be in r square form, I can write like even this, dB is equal to mu naught by 4 pi into I dl cross r cap. See, when I am using r cap, then there is no worry of writing r cube, it will be r square, because it is anyhow unit vector. So there is no issues. Since I am writing r vector, I am writing it as r cube below. So Abhishek came with a doubt. Sir, what is the difference between permittivity and permeability? See, permittivity is for the electrostatics, that is when the charge is at rest. Then what is the permission the medium is giving for the interaction of charges, that is called as permittivity. And permeability is the allowance which is given by the medium when there is a current flowing through a wire. So permeability is linked with the movement of charges, whereas permittivity is linked only when the charge is at rest, when the charge is not moving, it is stationary. I hope I could clear your doubt. So this is about the Bio-Savart law in scalar form as well as vector form. Trust me, this question may come. They will give you what is the simple question can be. Choose the Bio-Savart law, and there are 4 formulas giving. You don't confuse when you see r cube here. It may be r cube. See here r vector should be there, and here r cube, then r square will be there. So be very, very careful in choosing the correct answer. By a small thing you may lose marks, and you know very well about MCQ pattern. Do a mistake, 0, no step marking, right? So coming back to the next page. So yeah, application of Bio-Savart law. So by using the Bio-Savart law's application, Bio-Savart law just gave me an idea of finding the magnetic field for a current element. Now we want to find the magnetic field to a straight current carrying conductor. So if I have a straight infinitely long current carrying conductor and I wish to find what is its magnetic field at any point distance some r or something away from that, we can find it. See, let me assume that this is the wire. This is the wire, straight wire carrying current. Let me assume the current is carried in the upward direction, and let me take a small element dl. At any point here, maybe let me assume that from the center, this wire is infinitely long, it will have some center, right? So from center I am taking some point P. This is the point P, and I wish to find what is the magnetic field at this point P. Obviously, I know very well direction of magnetic field at P will be inwards. That I hope you have understood by now, that it will be inwards, right? So like this, inwards magnetic field is there. Okay. Now the question is to find the magnitude of magnetic field. Direction is already there. Fine. So what do we do? First step was to join this current element and the point, isn't it? And this was the angle theta. I hope you remember this. Theta was the angle which was made by the dl and r. This is r, right? Now let this distance, that is the perpendicular distance of the wire from that point, if I call it as a, You can call it as X, Y, Z, anything. I'm calling it as A. If it is called as A and this angle is phi. Now what is phi? Phi is the angle subtended by the point P. Listen to me very carefully. Angle subtended by the point P with the current element. So if current element is below, it will further increase. If it is near the center point, it will further reduce. I hope you are understanding. So phi is the angle that the point, this point P, makes with the wire, makes with the current element actually. So if I take the topmost end and the bottommost end, then let me take this as phi 1 and let me take this as phi 2. Obviously, if it is infinite, it will keep on increasing. Can you feel? It is here 0 degree, some 2, 3, 4, 5, 6, 7, 8, 20, 30, 40, 50. So as it goes far, definitely this angle will keep on increasing. I hope you are understanding this point. So again, I am not going to derive the complete derivation, but I am going to tell you the final value of it. So we will get the value of magnetic field B as mu naught I by 4 pi A. Remember, mu naught I by 4 pi A into sine phi 1 plus sine phi 2. Don't confuse in this, as simple as it is. Anyhow, derivation is not required for this term 1 syllabus. If someone is sincerely listening to me in this video and just knowing the formula correctly, the concepts correctly, they can score good marks actually in the board examination, because there is no derivation, you have to not write pages and pages. If you know the formula correctly, know the concept correctly, tick and you will get the marks. Okay, coming back. So mu naught I by 4 pi A, where I is the current carried in the wire, A is the distance of the point where you are finding the magnetic field. I should say perpendicular distance from the wire. I should not say any distance. It is the perpendicular distance of the point from the wire. And phi 1 is the angle subtended by the point P in the lowermost end, and phi 2 is the angle subtended by the point in the uppermost end. So if the wire is infinitely long, if the wire is infinitely long, very long, then what happens? Phi 1 as well as phi 2, they both become 90 degrees. I hope you understand this. Very far, 90 degree. So sine phi 1 is equal to sine phi 2 will become 1, isn't it? Sine 90 is 1. So what will happen here? See the equation. B will become equal to mu naught I by 4 pi A into 1 plus 1, that is 2. So B, magnetic field, will be equal to mu naught I divided by 2 pi A. So this is the value of magnetic field for an infinitely long straight current carrying conductor at any point A distance away from it. I hope you are understanding this. Mu naught I by 2 pi A. This is the value of magnetic field for any point near the straight current carrying conductor if the wire is infinitely long. So I hope this is clear. This was about the magnetic field due to a straight current carrying conductor by using the Bio-Savart's law. Now let us go to the next page and learn the second application of Bio-Savart law, which is to determine the magnetic field due to circular loop carrying current. So I may have a circular loop, like this, which is carrying current. See, I have drawn it in this dimension. Actually, it is not circle like this. I am drawing a circle and keeping it something like this. So that's why I am drawing in this way. If you want, I can draw it once again. Something like this. But don't think it is ellipse, it's circle only. If I want to find what is the magnetic field at this point, same point P, due to the, current element here, dl, and I will join this point, let me call it as r, and this is, the radius, that is a, and this is distance of the point from this center of this circle, let me call it as x. So see carefully, x is the distance of the point where you are finding the magnetic field from the center of the coil. A is the radius of the coil. R is the distance between the current element and the point where you are finding the magnetic field. So when you solve this, when you solve and find, again it is a big derivation, we don't have time to derive it now. I am going to tell the direct final formula to you. So if you find the magnetic field at this point B, that magnetic field B will be equal to, it will be equal to mu naught I into A square divided by 2 A square plus X square power 3 by 2. Again, very important formula, you may have questions from this. Believe me, you may have questions from even this. So remember the formula, mu naught I A square by 2 into A square plus X square power 3 by 2. Now, there are certain scenarios. If this point P comes to the center, that is x becomes 0. If x becomes 0, that is I am finding the magnetic field at the center of the loop. If that happens, if x becomes 0, put in the formula, B will be equal to mu naught I A square by 2 into A square power 3 by 2 will become A cube, and this will get cancelled. You will get the magnetic field is equal to mu naught I by 2A. Questions are there based upon this in sample paper also. In sample paper also you have questions based upon this. I will repeat once again that magnetic field at the center of the circular carrying current, that is a loop, will be equal to mu naught I by 2A. Students, what mistake they will do, since they hear the word circle, they will somewhere think pi has to be put somewhere. So what they will do, they will put pi here, 2 pi A in this equation, and for straight they will use 2A. Don't do that mistake, right? A is the radius of the circle, so magnetic field is mu naught I by 2A. This is for the condition when x is equal to 0. There is also a possibility that x is very much bigger than A. If x is much bigger than A, that A is negligible, A can be neglected, then what will be the B? B will be equal to mu naught I A square divided by 2 into A will become 0, so it will be x cube. This is the expression for the condition when you want to find the magnetic field at a very far point compared to the center. From the center of the coil, the point is very far. So x is much bigger than A. In that case, the magnetic field will be mu naught I A square by 2x cube, and this is mu naught I by 2A. I hope you know all these things and you are revising well now. Let us go to the next page. Okay, let us solve the question. So the question is magnetic field in a circular loop of diameter 0.1 meter carrying current of 1 ampere is how much? Come on guys, let us see who is solving. It's a very basic simple question. That's why I want you to solve by yourself, and let me see how many of you are really present and there, because I can very well see how many of you are coming for the classes. You are simply coming, owning and going, putting attendance, it won't work out. Anyhow, it is for your betterment only. Let us see. So I am waiting for you to reply. Let us wait. I'll wait for a minute. I hope you are solving. Any solutions? I am waiting for the answer, guys. Simple question, that's why I am asking you to do. No answers. Okay, so answer is given by Abhishek. He's saying option C. I hope he is correct. Abhishek says option C. So, yeah, one more person is replying option C. So, we have more votes for option C. Yeah, Kavya is saying option C. So, let us see. Let us try to just check whether option C is right or not. So, magnetic field in circular loop of diameter 0.1 meter. So, 0.1 meter diameter means R is 0.05 meters. Current I is given as 1 ampere. And they are asking you to find the magnetic field in a circular loop. We know the formula very well, that magnetic field is equal to mu naught I by 2a. So, a is the radius, in this case a is 0. So, mu naught value would be 4 pi into 10 to the power minus 7. The current value is 1 ampere divided by 2 into a is 0.05. So, it will become 0.1 and it will go above. So, it will become 4 pi into 10 to the power minus 7 divided by 0.1, and when you solve this it will become 10 to the power minus 6, and yeah, exactly, it will come as 1.25 into 10 to the power minus a Tesla. Very good, correct. So, let us go to the next question. Okay, next topic, Ampere's circuital law. So, Ampere's circuital law, it was to be very frank, very similar to Gauss law. Like how Gauss law is there in electrostatics, we have Ampere's circuital law in magnetism. So, what Gauss law said? He drawn a Gaussian surface and said that the net flux through this Gaussian surface would be 1 by epsilon naught times the charge enclosed. Similarly, here we will draw something called as Amperian loop. Sorry, we will draw something called as Amperian loop covering the current. There we were drawing Gaussian surface to cover the charge. Here we will draw Amperian loop sorry, covering the surface, that is covering the current. So, what this law says, listen to that first. It says that line integral of B dot ds, B is magnetic field, ds or you can say dl, whatever, magnetic field into the length, for a closed curve is mu naught times the current flowing through it, that is integration of B dot dl is equal to mu naught into I. That's it. That is Ampere's circuital law. With the help of Ampere's circuital law, you will come to know in the next page that we can even find what is the magnetic field due to a solenoid. So, I hope you know by now what is a solenoid. Solenoid is just the copper wire wound in the form of a cylinder which behaves as a magnet when the current is passed through it. So let me just draw one for you. So something like this. When you connect this coil with the source of EMF, that is the source of voltage, then current starts flowing through it, and when the current starts flowing through the solenoid, it starts behaving like a magnet. It has a magnetic field around it. So what is the magnetic field coming inside a solenoid? That was actually found by the Ampere Circuital law by taking one loop here, and I hope you remember all the derivation. We found this, and we found the value of magnetic field as mu naught Ni. Mu naught Ni. Please remember that N is the number of turns per unit length, not the number of turns. Number of turns per unit length. That is the small n value. One more thing, you must know that if I connect a cell with a solenoid, which side of the solenoid behaves like a north pole and which side behaves like a south pole. That also you should know. So if you see here, the positive terminal is there. So the current starts from here. Current goes like this, current goes like this, goes above, again goes above, like this it will go and come back. Very important thing I am going to tell you now, very important thing. Pay attention. So what happens when we have the direction of current like this? You will say the direction of current is anti-clockwise. So it looks like this. On this side it is anti-clockwise, anti-clockwise, anti-clockwise. Right. See, anti-clockwise for the person seeing from your side, for me it is clockwise. So always if you see from one side, if it is clockwise, from the other side it will be anti-clockwise. Okay, not to confuse you much now. So here the current is going anti-clockwise. So anti-clockwise side, the anti-clockwise side, see, it will become like a north pole. You can remember like this. Like this. So north is anti-clockwise. You see properly, the current is going anti-clockwise here. Same way, it is behaving like a north pole. So which place the current is entering in the anti-clockwise way, that end of the solenoid behaves like a north pole. And same way, this side it is clockwise. You see, it is becoming clockwise. So when it is becoming clockwise, then it would be the south pole. Remember like this. You see, clockwise. So if it is a clockwise side, that side will behave like a south pole. You will come to know also in the coming lecture, coming next video of EMI and AC. It will be having its own importance to know south and north. Yeah, so Harshavardhan is asking, what is the difference between a solenoid and toroid? See, solenoid is present in the longitudinal way, like a spring. You can imagine a spring is there like this. Toroid is the same solenoid turned in the form of the circle. I will tell about that in the next page. Let me come there. So I hope the solenoid is clear to you. If I go to the next page, what Harshavardhan is asking, it is about toroid. So now I am going to tell about magnetic field due to toroid. And what is that? So first, what is a toroid? Like what he has asked, let me explain to you. It is just take one solenoid, bend in the form of a circle. So I had a solenoid like this, and now I just bent it. How it became, you see? Like this. This is called as toroid. So solenoid, toroid are similar things. The difference is solenoid is straight and toroid is bent in the form of a circle. In solenoid, the magnetic field inside we found it was mu naught Ni, and all the other places outside the solenoid magnetic field is negligible, 0. Same way in toroid, inside the toroid, on this tubular area, we call it as tubular area. In this tubular area, the magnetic field is same, mu naught Ni, and inside this toroid magnetic field is 0, outside toroid magnetic field 0. Magnetic field is only in the annular, that is tubular region. Only in the tubular region we have the magnetic field. There is no magnetic field inside this region, that is this region, no magnetic field is there, no, nothing. And here also no magnetic field is there. Magnetic field is only in the tubular region. Same way for solenoid, magnetic field is only in the inside of solenoid. Outside solenoid there is no magnetic field. It is negligible. So we don't consider that. Once again I am repeating, N, many students are taking it as number of turns. It is number of turns per unit length. I told in the previous page also. So I hope you are clear with what is toroid and what is solenoid. So let us go to the next page and take one question. Right, the question is, a long solenoid carrying a current produces a magnetic field B along its axis. If the current is doubled and the number of turns per centimeter is halved, then the new value of magnetic field is how much? So this question, once again, I wanted to solve. I'll wait for a couple of minutes and I'll expect you to give me the answer. So let us see how many of you are active. Waiting for the answer. Okay, so first option has come, A. Good, Saravanan. So Saravanan says it is A. Anybody else who has got any answer? Yeah, answers are flowing inside. It is A. Yes, Abhishek says it's A. Anybody else? So the people who have attended, that is attendance wise, people are many. But when it comes to question, I can see only 3, 4, 5 people are responding. Others, I don't know whether they are still there or they have left for something else. Mr. Tarun, you are not at all responding. Yuvan, not responding. Even Mridula, Kritika, Ajay, you are just present. As per this, not replying to any of the answers. How I will know whether you are active or you are gone somewhere? Okay, so options are coming as A. I think the answer A is correct. In this question, they have given about the solenoid, magnetic field is B, and if the current is doubled and the number of turns is halved, that is, the current is doubled means I dash is 2 times of I, and number of turns per centimeter, that is number of turns per unit length, N dash is N by 2. Then what happens? We know that B for normal solenoid it is mu naught Ni, and in this case B dash will be equal to mu naught N dash I dash. So B dash will be equal to mu naught. Instead of N, I will write N dash, I will write N by 2. Instead of I dash, I will write 2I. 2 gets cancelled. I am getting same mu naught Ni only, and that's what is B. So can you see how simple questions can be? Sometimes this question can come in the examination. This kind of question can come. It's not tough, but the people who know this formula only can write the answer. If you don't know this formula, forget, lost. So please understand this. Let us go to the next page. So Orient, okay, you are Tarun, fine, right. So let us go to the next page, and we are coming to magnetic Lorentz force, next concept. So now you want to know that what happens to a charge when it is kept in a magnetic field. So if we have a charge, and suppose charge is coming in the magnetic field with velocity v, what happens to it? So for that, just let me take the 3-dimensional axis. And let me take the magnetic field. Let me take the magnetic field on the x-axis. Magnetic field is on x-axis. very sorry. So let us assume that the charge Q entered the magnetic field making some angle theta here like this with some velocity v. So it was found that whenever a charge is entering with some velocity v in the magnetic field, it is acted upon by a force. So once again I will repeat, whenever a moving charge is entering inside a magnetic field, it is acted upon by a force, and that force is called as magnetic Lorentz force. So what is magnetic Lorentz force? It is the force that acts on a moving charge, when it is kept in a magnetic field. So that force acts in the direction which is perpendicular to the plane of this. See, if it is v, it is definitely acting in x, z, if I say xz plane. So if velocity is in xz plane, then obviously force will be in the y axis. If the velocity would have been in x, y plane, then the force will be in z axis. So what I am trying to say, that force which is acting, it always acts perpendicular to whom? To v and b plane. So force formula comes F is equal to QVB sin theta. Why I am saying sin theta? Because this will become V sin theta, B and this thing. So if I write in the vector form, it will become F vector is equal to Q into V vector cross B vector. This is the magnetic Lorentz force. So magnetic Lorentz force is the force that acts on a moving charge when it is kept in a magnetic field. So I hope you are clear in this, a very basic thing. Let us go to the next part, which is Fleming's left hand rule. Obviously, so when I taught you about this Lorentz force itself, you understand that Fleming's left hand rule is to determine the direction of the force. So as I said you, that if you have two things, one thing is velocity, or I should say the charge movement, and one thing is magnetic field. So to understand or to find the direction of the force, you need to stretch your first finger, your middle finger, your thumb mutually perpendicular to each other of your left hand, not right hand. So of your left hand, the first finger, the middle finger and the thumb are stretched mutually perpendicular to each other in such a way that the forefinger is giving direction of magnetic field. The middle finger is giving the direction of current. Current means if the electron is moving, like this, then the current will be in the opposite direction, obviously. If proton is moving like this, then the current is in the same direction, isn't it? So just by the determination of whether the proton is moving or the electron is moving, you can find direction of current. So if the middle finger is giving direction of current and the first finger is giving direction of magnetic field, then the thumb will give the direction of force which acts on the charge. So this is the charge, it is moving, magnetic field here, its velocity is here, that is the current is going in this direction, it will be lifted upwards, right? So that is the Fleming's left hand rule. If you stretch, if I am drawing some diagram like this, the other fingers, how many fingers you have? 5, right? Yeah. So this is the first finger, this is the middle finger, this is also perpendicular, this is also perpendicular, and these two are also perpendicular. So this gives the direction of magnetic field, this gives the direction of current, this gives the direction of force. Remember this, as simple as it is. One more thing I want to tell you before going to the next page, that I just told you when a moving charge is kept in a magnetic field. Already you know what happens to a charge when it is kept in electric field. So need not to have a moving charge. If even a stationary charge is kept in electric field, there will be a force acting on it. I have told you already that if there is electric field like this and you are keeping a charge electron like this, it will start moving in the opposite direction, negative charge. And if you have a proton like this, it will start moving in the same direction of electric field. So a stationary charge starts to move And with what force? That force will be equal to QE. I hope you remember this. QE, charge times the electric field. So if you are keeping a moving charge in a region where we have both electric field and magnetic field, then the net force acting on it will become equal to QE plus Q into V cross B. V cross B. So if I take out Q outside, it will become E plus V cross B. This is the total force that acts on a moving charge if it is subjected to electric field as well as magnetic field. I hope you have understood this. So let us go to the next page, where we are going to take one question, a very basic question once again. A proton charged plus E enters a magnetic field of strength B with speed V parallel to direction of magnetic lines of force. What is the force on the proton? Solve it, guys. What is the force on the proton? Very, very simple question. Once again, a very simple question. You can answer instantly. The moment you see this question, you can answer it if you have understood the concept. If your concept is clear, it is the simplest question of the day. Believe me. Waiting for the answers. So Karthikeyan is saying hi now. Why Karthikeyan? Came late. Will a static charge placed in magnetic field move? Never, Abhishek. This question you are asking. Surprised. A static charge kept in magnetic field will remain static. Only a moving charge kept in magnetic field moves. Static charge moves only in electric field. If electric field and magnetic field both is there, obviously by electric field starts moving and magnetic field will again push it. I hope you have understood this. Fine. So C is flowing. I hope you are not referring something and telling these answers and you are doing it honestly by yourself. If so, excellent. All of you are right. The option is C. The question is damn simple. Yeah. So proton of charge E enters the magnetic field. So what I was trying to say, in this question they have given the proton is entering in magnetic field B with speed V parallel to the direction of magnetic lines of force. If the direction of the movement of the charge is in same direction of that of magnetic field, theta will become 0. If theta becomes 0, we know the force F is equal to Q V B sine 0. Sine 0 is 0, phi force is 0, isn't it? As simple as it is, nothing is required. Simplest question again. So let us go to the next page, which is motion of charged particle in uniform magnetic field. So in the previous page we have talked just about that if you have a moving charge kept in a magnetic field, it will be subjected to some force. We have not talked about how the movement will be there. So let us assume there is a magnetic field. I am assuming a inward magnetic field into the plane. And let me assume that there is a charge which is kept inside this magnetic field which is moving. So let me assume there is a charge Q and it is kept somewhere here, okay, and this Q is trying to move in this direction. See, very beautiful concept. Be attentive, listen to me very carefully. A simple but very important concept. Now this charge is moving upward. Try to find what will be the direction in which this charge will be subjected to force. So I am using my left hand, magnetic field inwards, Q is having the direction of current because it is plus Q, upwards, my force will push it in the left side, isn't it? So this charge which is supposed to go straight, instead of going straight, it will start taking a turn and enter like this, isn't it? Because it is getting pushed from the left side towards the right, like this. Again it comes here, it starts moving like this. Now this charge which was moving in this direction, let us see, again put your hand, magnetic field, current, it will be pushed, see magnetic field is there, current is there, push downwards, now it will turn like this, Are you able to feel? Instead of going straight, it will take a turn. Once again, it is trying to come down. See the magnetic field, current, it will push towards the right. So once again, instead of going straight, this charge will take a turn and go like this. Again coming here, trying to go straight, it won't be able to go straight, force will make it to go like this instead of going straight. So see what is happening. This charge, which was left to go straight in the magnetic field, starts moving in a circular path. One thing very important, I made sure that the charge, the velocity of the charge is perpendicular to the magnetic field. This is the magnetic field, this is the charge. See, they both are perpendicular. Definitely you can ask me, sir, what if the charge is not entering perpendicular? I will tell you the next page. But now understood that if a charge is kept in a magnetic field which is perpendicular to the velocity of the charge, it will start taking a circular path and start taking a turn like this. It will keep on moving in a circular path. If it is moving in a circular path, it must have some radius. Yeah, it will have some radius. We can find very easily. Since it is moving in a circular path, it will have some centripetal force, mv square by r. Who will provide the centripetal force? Obviously, your Lorentz force will provide, that is qvb sin theta, and we have taken theta as 90 degree here, so qvb sin 90 degree. Solve this, vv gets cancelled, you will get r is equal to mv by qb. This is the formula of radius of the circle which the charge will be moving. I hope you are understanding. Very beautiful, simple concept, that if a charge is going in a moving charge is going in a magnetic field, going straight will not be able to go straight, rather start going in a circular path with a radius of mv by qb. Fine. If I want to find what is the time period of this revolution, time period we know it is equal to 2 pi r, distance covered, by the velocity v. Now I can substitute the value of r, which is equal to mv by qb. Vv gets cancelled, sorry, already when v is here, so this v and v gets cancelled. I get time period is equal to 2 pi m by qb. I can find the formula of frequency also. Frequency is reciprocal of time period, 1 by t, and that will be equal to qb by 2 pi m. So any charge which is moving in a circular path, it will have radius of mv by qb, time period of 2 pi m by qb, and frequency of qb by 2 pi m. If you ask me, sir, do I need to mug up this and go in the examination? No, my dear children, no need of mugging up. You just want to remember this thing. How much time it took to derive? It hardly took a minute, right? So you can immediately derive in the examination hall itself. Because if you make a mistake, instead of mv by qb, take qb by mv, it will become wrong. And believe me, the question paper setters are very clever. They will give the option such that it will be qb by mv also, mv by qb also. So you will do very confidently, get a wrong answer and tick and come. Don't do that. Okay? So if you are not able to remember this formula, remember this alone: centripetal force mv square by r, Lorentz force qb sin theta. Equate both, get the answer. As simple as it is. So if you have understood this motion of charged particles in a uniform magnetic field, let us go to the second condition of it. Okay, before that one question is there. So I hope you are there, and obviously you are going to solve this. Question is, a proton and an electron with same momenta means momentum, enters in magnetic field in direction at right angles to the lines of force. Radius of the path is followed by them will be same. Okay, reason is electron has less mass than proton, obviously, but is this reason for this assertion? Check it out. Check it out. I am waiting for your answers. See, this kind of questions once again can be expected in the board examination, assertion and reasoning type. Yeah, waiting for the answer. No browsing, no googling, do it by yourself. Not able to get, tell in the comment box as doubt. I will tell you what is there in that. There is no browsing required for this question, please. Any answers? Answers started flowing inside. Option is C. So, okay, no, it has previous answer. So now the answer is only B. Harshvardhan says option B. Okay, good. Anybody else? Yeah, option B, Tarun. Option B, Abhishek. Option D, Devendran. No, Devendran, check your answer. Kritika says option B. Yeah, option B sounds correct to me. Please pay attention here. A proton and an electron with same momenta enter in magnetic field in direction at right angles to lines of force. Let us see. So now what is going to happen? A proton and an electron with same momenta are going to enter in the magnetic field. We know the value of R, that is equal to mv by qb. What is mv? Momentum. So I can write R is equal to p by qb, that is momentum by qb. Now R, the radius of the paths followed by them will be same. Obviously it will be same. If they have same momenta, obviously there is no change in the q and b, isn't it? A proton and electron, they will have just their different, q will be equal to plus c and minus c, but does not change the magnitude of it. So R will not change, isn't it? See, one thing may go in the clockwise direction, one thing may go in the anti-clockwise direction. That's what will happen. Are you getting a point? One thing may move like this, and one thing may move like this, but both will have same R. I hope you're understanding this. So the first statement is absolutely correct. Electron has less mass than proton. Yeah, but it is not the correct explanation of this. So option B is obviously correct. Good guys, let's go to the next question. Okay, one more assertion reasoning. If a proton and an alpha particles enters uniform magnetic field perpendicularly with the same speed, the time period of revolution of alpha particle is double than that of proton. A is alpha particle, guys, don't confuse. A is alpha particle, okay. So let me wait. Solve it. Come on, make it. Last chance, last practice, last revision. Thereafter you will have the board examinations. Waiting for the answer. Very good question actually. It's not very easy, but it's not tough either. Waiting for the answer. Any answers? Okay, so option A, which is given by Abhishek. So Abhishek says option A. Let us check. Okay, anybody else? Okay, Tarun says option A. Tarun, don't follow. Okay, anyhow, option A is the answer by both of them. Anybody else? Harshvardhan says option D. Anybody else? Ajay says option is I think A. Okay, good. Let us see. So you should not think, you should be sure. Anyhow, this examination you can think and also write because there is no negative marking. But avoid that, guys, avoid that. If you are good in concept, no need of thinking much. Right. If a proton and alpha particle, first of all, I am very much sure some of you may not know what alpha particle is. I have told in the class also. Alpha particle is nothing but helium nucleus. So helium nucleus, what is the formula of helium nucleus? 2, 4. That is, it will have a mass of 4 and atomic number of 2. Now, why I am writing this? Because, see the question, proton and alpha particle enters an uniform magnetic field perpendicularly with the same speed. The time period of revolution of alpha particle is double than that of proton. First of all, we must know what is the time period of revolution. I have found in the previous page. What was that? T is equal to 2 pi m by qb. Now magnetic field is same. 2 pi is a constant. Check the m and q. For proton, what is T1? It will be 2 pi mass of the proton divided by q of the proton and b. Q of proton can be taken as E, isn't it? And mp, let it be mp itself. Find T2. T2 will be 2 pi mass of the alpha particle is 4. So it will be 4 times the mass of the proton divided by q. Q is 2. 2 times the q of proton into b. So 2 will get cancelled. So it will be actually 2 times. So finally see what you are going to get. You are going to get T2 is equal to 2 times of T1. That's what they are saying. Time period of revolution of alpha particle is double than that of proton. Exactly double it will be, isn't it? And reason what they have told, in a magnetic field, period of revolution of charged particle is directly proportional to the mass of the particle and inversely proportional to charge of the particle. Exactly correct. So option A is correct. I hope you are getting this. See, I am trying to make you practice all kinds of questions. That's why I am taking assertion reasoning questions. Many of you have told me, sir, we have doubt in A and R type of questions. We are able to do MCQ, but we are confused in A and R. I think now you are getting some clarity over the A and R. Okay, let us come to the next part, that is the motion of a charged particle launched at arbitrary angle. Same thing which I was talking about in the previous page, that if suppose it is not going, in the previous scenario what I took the magnetic field like this and placed the charge perpendicular to it. So it has gone and took the circular turn. But what is the necessity that it will always be circular? It will always be perpendicular. That is the motion, the velocity and the magnetic field. It may not be perpendicular also. So what I am trying to say, now if this is the magnetic field, I am going to project the particle with some deviation theta. This is V vector. Charge is projected at some deviation theta and I want to know how it will go, how it will behave. So you can see very clearly from here, this is V. If you resolve in two components, what will happen? This side I will have V cos theta, that is the parallel. This is the parallel component, V parallel I will write. V parallel, which is along the direction of magnetic field, and we have V perpendicular, that is equal to V sin theta, isn't it? So I can resolve my velocity into cos theta and sin theta, V sin theta, V cos theta, V perpendicular, V parallel. Now this particular charge Q is subjected to both V sin theta and V cos theta. Now see, V cos theta is acting in the same direction of magnetic field. You know very well that if the direction of velocity is same as magnetic field, it won't create any force. So there will be no motion due to V parallel. Motion will be there only due to V perpendicular, because that is only acting in the perpendicular direction of this magnetic field, isn't it? So R, instead of writing mV by QB, I will write mV perpendicular by QB, isn't it? So what is mV perpendicular? M into V is V sin theta, so mV sin theta by QB. So instead of writing mV by QB, I will write mV sin theta by QB, nothing, simple. Now time period is 2 pi m by QB. So instead of m, let me put the value of from here. Actually for deriving this t, this is only valid for the circular motion. So instead of doing that, let me do it from the beginning. That time period is equal to its radius 2 pi r by v, v which v perpendicular. So r I have found it to be 2 pi mv sin theta by qb, and V perpendicular is V sin theta. So, can you see one thing? Both gets cancelled. I get same T is equal to, which I cut now, 2 pi m by qb. What I am coming to say, whether you are projecting a particle, I mean perpendicular to magnetic field or at any arbitrary angle, time period will not get affected. It will remain same 2 pi m by qb only, because it does not depend upon the velocity. It just depends upon the mass and the magnetic field and charge. So, it will have the same time period. But how it will go, can you see? This thing will make it to go in circular path, that V sin theta component, and V cos theta component will push it this side. So, your motion will be helical like this. I hope you are understanding this. So, your charge, instead of going only in one place circular, it will start going forward, circular, forward, circular, forward, circular, forward, due to V sin theta as well as V cos theta. The distance between two successive circles is called as pitch. I have seen question coming from pitch also in the examination. I have seen this in the board examination sample paper. Question is coming from pitch. Pitch will be equal to what? This distance you want to find, that will be equal to time multiplied by this V parallel. That is V parallel multiplied by the time period. What is V parallel? It is V cos theta. What is time period? 2 pi m by qb. So, what is the pitch formula? Pitch formula will be equal to 2 pi m V cos theta by qb. Just remember this, or remember this V parallel by time period, you can always find this. So, this is the expression for pitch, this is the expression for R, and the same is the expression for time period, no change in that. I hope you have understood how a charged particle will behave when it is projected at an arbitrary angle to the magnetic field. Okay. So, let us go to the next page where we have a question based upon this. Okay, now I have come to the passage type question. So, we will have 4 questions connected to each other. Again, I have not taken the full passage, it will take the whole page itself. So, I have just taken some initial statements and the questions. The first question is, when a positively charged particle enters into a uniform magnetic field with uniform velocity, its trajectory can be a straight line, a circle, or helix. So, see, positively charged particle is entering into uniform magnetic field with uniform velocity, trajectory, its trajectory will be what? So, I have told you now, it can be a straight line if it is projected parallel to the magnetic field. It can be a circle if it is projected perpendicular to the magnetic field. It can be even a helix when it is projected at an arbitrary angle. So, it can be 1, 2 or 3. Option B is correct. Next page. So, next question is, two charged particles A and B having the same charge, mass and speed enter into a magnetic field in such a way that the initial path of A makes an angle 30 degree and that of B makes an angle of 90 degree with the field. What is the trajectory? Trajectory of, actually here B should come. So, B will have smaller radius of curvature than A will have smaller radius of curvature than B, both will move along the direction of their original velocities, both will have same curvature. For finding this, see, it is very simple. We know very well that this mv square by r is equal to qb sin theta. It is mv square by r will be equal to qvb sin theta, isn't it? Because it is projected at an angle of 30 degree and 90 degree. So, that is why I am telling. So, see, if you see this equation, v and this gets cancelled, I get mv by r is equal to qb sin theta. Now, how this equation helps me? This equation clearly helps me to determine the r in terms of theta. So, if you see this, you will come to know that what are things are constant in this? Having same charge, same mass and same speed. So, if mass, charge and the speed all are same, then we can very clearly say that r and sin theta are inversely proportional. So, r is inversely proportional to sin theta, that is what I am coming to say. So, r of the first particle by r of the second particle will be equal to sin theta of the second particle by sin theta of the first particle. So, how much it will be? Sin 90 divided by, sin theta 2 is 90. right? So, sin 90 by sin 30, sin 90 is 1 and sin theta is 1 by 2, that is equal to 2. So, R1 is equal to, or 2R1 is equal to R2. That is what I am getting. R2 is equal to, or 2R2 is equal to R1, sorry, because it is 2, R2 will go here, it will come down. So, R2 is equal to R1 by 2. I get the radius of the second particle as half of the radius of first particle. So, obviously, B will have smaller radius of curvature than that of A. See, again I am saying, if the concept is known to you, this equating is known to you, these questions are damn simple. So, I have told you, centripetal force given by what? QEB sin theta. Why I have taken sin theta here? Why I have not taken as QEB alone? Because they have told it enters with some angle, 30 degree, 90 degree. So, it is arbitrary angle. That is why I have taken arbitrary concept. I hope you have got this. Next page. Yeah, electron having momentum 2.4 10 to the power minus 23 meter per second enters a region of uniform magnetic field of 0.15 Tesla. The field vector makes an angle of 30 degree with the initial velocity vector of the electron. The radius of helical path of the electron in the field shall be. Direct formula. R formula we know. R is equal to, sorry. So, in the formula of R is equal to mv sin theta by qv. mv sin theta by qb. So, what is m given? Actually, mv is given, momentum is given. So, directly you can put, instead of mv, you can put 2.4 into 10 to the power minus 23 into v. V is given, electron, the uniform magnetic field is given, and field vector makes an angle of 30 degree with the initial velocity of the electron. Okay, so if V is not given, then what we will do? Electron, okay, V is not required, sorry, mv is known, no? So, sin theta is 30 degree divided by q into b. So, q electron. So, if it is electron, q will be equal to 1.6 into 10 to the power minus 19, and b 0.15 Tesla. So, 0.15. Just put and solve this. If you solve it correctly, you will get the answer. And the correct answer, if you solve it, will come as 0.5 millimeter. That is the answer. So, just put the formula correctly, you will get the answer. And last question from this passage type. The magnetic field in a certain region of space is given by magnetic field equation is given. A proton is shot with a field of velocity 2 into 10 to the power 5 I cap plus 4 into 10 to the power 5 j cap meter per second. The proton follows a helical path in the field. The distance moved by a proton in the x direction during the time of one revolution in the yz plane will be how much? Okay. So, they are asking you to find the distance moved by proton in the x direction. See, what is that? This is also one skill of identifying what is being asked in the question. So, distance moved by the proton in the x direction. So, you remember this? This is what they are asking you, pitch. And I told you what is the formula of pitch, isn't it? Pitch, I told you, V parallel multiplied by time, isn't it? So, what is time? Time was 2 pi m by qb, and what is V parallel? V cos theta, isn't it? So, put all the values, 2 into 3.14 into mass. So, mass of the proton, you know very well, 1.67 10 to the power minus 27, they are given also 27 into V cos theta, this term, that is very important, V parallel. So, V parallel is given as how much in this? See, they have two things, in y direction 4 into 10 to the power 5, in x direction 2 into 10 to the power 5. Very wisely you have to choose 2 into 10 to the power 5 divided by q. Q will be given as 1.6 10 to the power minus 19, and b is given as this much, 8.35 into 10 to the power minus 2. So, just put in the equation everything correctly, you will get the answer, and the answer for this question will come as 0.157 meter. Solve it and check, you will get the same answer. So, this kind of question, again, if you know the concept of pitch, you can solve. So, I have told you how a question can come from motion of charged particle in arbitrary path, right? Passage type question. It has 4 marks. Remember that. So if you have left this topic and gone for the examination, 4 marks gone. So every topic is important, right? So one more question is there. A proton and alpha particle both enter a region of uniform magnetic field B, moving at right angles to the field B. If the radius of circular orbit for both the particles is equal and the kinetic energy acquired by the proton is 1 million electron volt, the energy acquired by the alpha particle will be how much? Okay, very good question. So what is given, you see, they have told once again a proton is entering, a proton and alpha particle. Alpha particle means helium, never forget that, 2, 4. Enters a region of uniform magnetic field B, moving at right angles to the field B. If the radius of circular orbits for both the particles is equal and the kinetic energy acquired by the proton is 1 MeV, what is the energy acquired by the alpha particle? First you have to relate both. So what is the value of kinetic energy? Kinetic energy to find, let us see the equation of R. R will be equal to mv by qb, isn't it? Or I can say momentum by qb. Now since I have the relationship of momentum, momentum is equal to root 2 times of kinetic energy, isn't it? Root 2 ke divided by qb. I hope you remember this. Actually it's root 2 mke, root 2 mke. So when you square both sides, you will get r square q square b square by 2m as kinetic energy, isn't it? This is the formula of kinetic energy. Now check for both once again, proton as well as helium. So for kinetic energy of proton, how much it will be? It will be r square q square b square by 2m. And kinetic energy of alpha particle, how much it will be? R square, instead of q, it will have 2. So 2q the whole square, 2q whole square into b square by 2 into m. M will be 4 here, 4 times the mass. So obviously this 4 and this 4 will get cancelled. You are going to get the same r square q square b square by 2m only. Are you getting my point? This 4 and this 4 will get cancelled. So it would be giving you the same value. So kinetic energy of alpha particle will be same as that of the proton, and proton they have given 1 MeV. This also will be 1 MeV. Yeah, there is a doubt asked by Harshavardhan. V cos angle, that is V cos theta, why you took I cap value, sir? Yes, in the previous question you are asking, I feel. So let us go to the previous question. So what Harshavardhan is asking, he is asking, in this question, I have velocity as 2 into 10 to the power 5 I cap plus 4 into 10 to the power 5 j cap. The proton follows a helical path in the field. So they are asking you, he is asking me why in the velocity I took this part alone and I did not consider this part. Thambi, please pay attention here. The distance moved by the proton in the x direction. What is I cap? Velocity in x direction. What is j cap? Velocity in y direction. When they are talking about x direction to you, why do you want to take the velocity in y direction? Magnetic field is in x direction. If suppose you would have given multiplied by or plus some 2 into 10 to the power minus 3 j cap, I will not take this value also, because I need to worry only about the x direction. Since they have asked me to find only about x direction, I took what is the velocity in x direction and what is the magnetic field in x direction. I hope I made your point clear. So let us go to the next topic, that is force on a current carrying conductor in magnetic field. So I know some of you may be tired by now and may be feeling like when the class will get over. My dear children, today class will go a little longer because we are going to see 2 chapters, isn't it? So definitely it will go at least half an hour to 40 minutes more. Please be patient. Please be patient. Remember that whatever you are learning, you are covering 2 chapters of physics. And believe me, I am not simply giving formula and going. You are seeing what I am doing. Each concept I am clearing and then question I am solving. So if you want this kind of service, definitely you have to put your time. So if you are planning to, okay, enough for today, I will go and sleep, I will see later, that later will never come. So hold on, cooperate, only then we can finish. So first of all, we are already like it's last minute preparation. In last minute preparation also you want to take rest, then God can save you. So coming back, force on a current carrying conductor in magnetic field. So we learned about how the force on a charge comes when it is kept in magnetic field. Now we want to learn how the force on a current carrying conductor comes. We have learned this in the 10th class also, that if you have a conductor like this having some current by the battery, suppose this is the current direction, and suppose this is kept in some magnetic field. So we know very well that if a current flows in a conductor, it will be acted upon by some, it will have some magnetic field. If the current is passing through any place, magnetic field will be there. So one magnetic field is coming by the current in this conductor. One magnetic field is coming by the external magnetic field. These two magnetic fields will interact and there is a force acting on this conductor. How much force will be acting? The magnitude is F is equal to I into L cross B. That is ILB sin theta. F is equal to ILB sin theta. This is the force acting on a current carrying conductor kept in a magnetic field. What is the direction? Yeah, obviously direction can be found out by our left hand rule. So we can use the same thing and find a direction. So let us go to the next page. Simple thing, ILB sin theta, force. Yes, force on two parallel current carrying conductors in magnetic field. So what if we have two conductors and both of them are carrying current? So if we have two conductors carrying current, see, very important, very important, very easy. This is conductor 1, conductor 2, current I1, current I2. If current I1 is going in this wire, definitely on the wire 2 it will have an inward magnetic field. Do you agree with me? Current 2 is taking current in upward direction, wire 2. Magnetic field on wire 1 will be in the outward direction. I hope you are understanding this. So here we have inward magnetic field, here we have outward magnetic field. Distance between the wire is, let me take it as A, your wish you can take it as R also. Now current carrying conductor, magnetic field, what will happen? Force will act. Put your left hand rule, magnetic field inward, current above, force in this direction, F2. How much will the value of F2? F2 will be equal to, we know that ILB sin theta, isn't it? So it will be equal to I2 into length L into B. B1, isn't it? Magnetic field is coming due to the first wire, so B1 I will write. And what is the value of B1? We can find the value of B1. We know by the straight current carrying conductor, magnetic field at any distance A, that is B1 will be equal to mu naught I1 by 2 pi A. I hope you remember this. Today we have learned that magnetic field due to a straight current carrying conductor is mu naught I by 2 pi A. So mu naught I by 2 pi A will be B1. Same way, what will be B2? B2 will be mu naught I2 by 2 pi A, isn't it? So if I put the value of B1 here, F2 will become equal to I2 into L into mu naught I1 by 2 pi A. Same way, if I find the value of F1, check, magnetic field outwards, current upwards, it is going this side, that is towards this F1. And what will be F1? F1 will be equal to I1 into L into B2. So I1 into L, instead of B2 I can put mu naught I2 by 2 pi A. See, both are same. Both are same. Mu naught L I1 I2 by 2 pi A. So this force with which both are getting attracted, that force will be same. That is F1 will be equal to F2. You can name it as F, and that will be equal to how much? It will be equal to mu naught I1 I2 L by 2 pi A. This is the formula of force. And you can find force per unit length also from here. F by L will be equal to mu naught I1 I2 by 2 pi A. Force per unit length. So when two wires are carrying current in the same direction, they will be attracted towards each other. And if two wires are carrying current in the opposite direction, you can see by yourself, it will be repelling each other. It's very simple. And the force per unit length will be same, that is mu naught I1 I2 by 2 pi A. I hope you have understood this. Yeah. So let us take one question. A square loop ABCD carrying current I is placed near and coplanar with a long straight conductor XY carrying a current I. The net force on the loop will be how much? So if you are not able to see the diagram clearly, this is ABCD loop. I will just redraw it for you. So this is, I am drawing it here separately. So this is XY wire and this is Y. This is the loop A, B, C, D. Length is L and this length is given as L by 2 and this length is once again L because it is a square, and current is flowing in this direction I clockwise. Just try to find this answer. Do it honestly. I will be back in 2 minutes. Don't go anywhere. Solve it and tell me the answer. Yeah guys, I am back. I hope you are solving this. Any answers? Any answers? Any answers? I am waiting for the answers. A square loop ABCD carrying a current I is placed near and coplanar with a long straight conductor. This kind of questions are common. Even you have an NCERT textbook, this kind of questions. I am expecting your answer if you are there. At least if you don't know, put a doubt there to make me understand you are there. So Harshavardhan says option C. Option C is the answer by Harshavardhan. Anybody else? Anybody else? If you have not left the class and you are there in the class, at least put a, if you are not knowing the answer, just put doubt so that I can explain it to you. I am waiting for you to reply. U1 is saying option B. Okay. So U1 says option B. Harshavardhan says option C. Anybody else? Doubt is told by Kavya. Good. All the other people, I think they are just for the namesake you came for attendance. Guys, where are you? Okay. Abhishek says option C. Okay, okay. Kritika, if you are there, Ajay, if you are there, Devendran, guys, if you are there, expecting the answers from you, Ajay says doubt. Okay. Very good question. This kind of questions definitely can be expected in the examination. Okay, let us not wait for other people and let us try to note the answer for this question. Right. So if you see here, there are two parts, AB, CD. Obviously, BC and AD, they are equidistant, right? Point B, point A are equidistant. Point C, point D are equidistant. So the force on BC will be equal to AD in opposite direction. Here the current is going like this, here the current is coming like this, so they will cancel out each other. Our concern is only the force which is acting on the wire AB and the force acting on the wire CD. Tell me one thing, if you have a straight current carrying conductor like this, you have a wire here taking current in the same direction, what will happen? How the force will be? How the force will be? Attractive, right? You have a wire taking current in the downward direction. How the force will be? Repulsive, isn't it? So force are in opposite direction. If force are in opposite direction, the net force can be found out by greater force minus smaller force. So greater force you can find for AB. What will be the force on AB? Just now we have seen. So force on the AB, the formula you know, it is mu naught I into small I into length, anything they have mentioned? Okay, length is given as L. So mu naught I into L divided by 2 pi into this distance, it is L by 2 given, isn't it? Minus mu naught I L by 2 pi, instead of L it will be L plus L by 2, 3L by 2, isn't it? 2 gets cancelled, 2 gets cancelled, take the LCM, actually LL gets cancelled, here the LCM will be 3 pi. So down 3 pi is going to come, so definitely this answer cannot be there, option can only be A or D. Let us see. So if you do this, so it will become 3 minus 1, it will be 2, so 2 mu naught I. Can you see the answer, how it has come? Simple question, if you know the concept. None of you could say the correct answer, nothing wrong. If you have understood the concept, at least next question comes like this, you can solve. That's what we want, right? Okay, let us go to the next page. Force on a current carrying conductor, again on a question based upon that. Two long parallel wires are at a distance of 1 meter. If both of them carry 1 ampere current, what is the force of attraction per unit length? They are asking you to find what is F by L. So you know the formula of F by L. F by L formula is mu naught I1 I2 by 2 pi A. So you know all the values, just put in this equation. Mu naught is 4 pi 10 to the power minus 7, I1 1, I2 1 divided by 2 pi into A, distance between them again 1, 2 pi will become 2 times 2 into the power minus 7. D is the correct answer. Damn simple question. Just if you know the formula correctly, you can find the answer. Right. Next question or next topic. Torque experienced by the current loop in the uniform magnetic field. So what happens on a loop, that is a wired loop like this, if it is subjected to a uniform magnetic field? Once again, I am not going to derive that, what is going to happen, but you know very well, torque will act on it, and how much torque will act on it? That will be equal to BINA sin theta. Now what is N here? Capital N I have written, be very careful, not small n. It is the number of turns, not number of turns per unit length, number of turns. What is B? Magnetic field. I, current taken by the loop. A is the area of the loop. Theta is one important thing. It is the angle between magnetic field and area vector. What is the meaning of area vector? area vector will be the normal of this area. Suppose this area is here, so no problem, here theta is 0 degree, isn't it? So I mean to say that this angle, what this normal makes with the magnetic field. Please make note of this. This is the formula of torque, BINA sin theta. You will know in the next chapter, that is B into I into A, BIA, or I should say NIA, sorry, NIA. NIA is also called as magnetic moment, M. I into A, magnetic moment is the multiplication of current into the area of the loop. So NIA is called as magnetic moment, it is a vector quantity. So we can write from here tau is equal to M vector cross B vector, that is MB sin theta, MB sin theta. So if any loop is kept, in the magnetic field, torque acting on it will be equal to MB sin theta. So please understand this. Okay, now we have come to we are entering the last part of the chapter. Don't worry about it much. We are going to finish soon. So we have moving coil galvanometer, where you have this kind of setup. So MCG, what happens? You keep a coil. We know very well, if you keep a coil in the magnetic field now, it will be acted upon by a torque, right? Now in this case, we have to keep the coil very carefully in such a way that it is acted upon by field in a radial manner. So here the magnetic field will be radial. Can you see there are curved magnets are there? Why? Because I always want theta to be equal to 90 degree. Why I want that? See, tau is equal to NIBA sin theta, right? If theta is 0, tau is 0, no torque. If theta is 90 degree, tau is maximum. How much that is? NIBA. So I want always the maximum torque to be there. So for torque to be maximum, I must give the theta always 90 degree. If theta is always 90 degree only, it is possible. So that is the reason I am giving a radial magnetic field such that always theta remains 90 degree. Again, a theoretical question may be asked from here. What is the use of radial magnetic field? You must say it is because of the theta to maintain 90 degree, right? So now what happens in this galvanometer, when you are placing a coil in the magnetic field, it will be acted upon by a torque. That is called as deflecting torque. Torque deflecting. And what is that value? We know very well, NIBA. Sin theta is 90 degree. Sin 90 is 1. When your coil is being rotated, see, coil is mounted in a spring. Okay. Now you know very well, if you rotate the spring and leave it, it will once again come back. Why it comes back? It has elasticity. So it will have a restoring force. So there will be a restoring torque coming. And this restoring torque, it purely depends upon how much twist you are giving. If you are twisting less, it will come back less. If you are twisting more, it will come back more. So this restoring torque is directly proportional to angle of twist, alpha. What is alpha? It is the angle of twist. If you twist more, it will have more torque. If you twist less, it will have less torque. If I remove proportionality, I have to add a constant, and that constant is called as K. K alpha, spring constant. So restoring or torsion constant, whatever I want to say, K is called as spring constant or torsion constant. So we know now that restoring torque is K alpha and deflecting torque is NIBA. If I equate both, I will get K alpha, because both will be same. K alpha will be equal to NIBA. From here you can know what is alpha, angle of twist, that is equal to NIBA by K. This is the equation of angle of twist. It is the equation of angle of twist, and we can also find what is the value of current from here. Current I will be equal to K into alpha divided by NBA. Now K by NBA is called as G, capital G. It is called as galvanometer constant. So I will be having I is equal to G alpha, where G is the galvanometer constant. I hope you know what is a galvanometer. It is the electrical instrument used to measure a very feeble amount of current. If the current is passing through a machine, you must be able to detect that. So if you have an ammeter, it will detect only some good values. If you have 1 microampere going, it won't detect, it won't say anything. But galvanometer, it will deflect. That's what our concept is. Little bit of current passing, it will deflect it, because we know if the current is passing through the wire, it will be acted upon by a torque, because current carrying conductor kept in a magnetic field, force will act, torque will rotate it. So it will show the reading to you. That's the concept. So we know I is equal to G alpha, where G is the galvanometer constant. Right. So let me go to the next page now. Sensitivity of galvanometer. So galvanometer has some sensitivity that is called as voltage sensitivity and current sensitivity. Now what is sensitivity first of all? Sensitivity means we want it to show large deflection with even very less current. Sensitivity means it is the large deflection for even less current. See, not only that, sensitivity as a formula, it will be twist angle per unit current or per unit voltage. So angle of twist per unit current is called as current sensitivity. This is angle of twist per unit current, and angle of twist per unit voltage is called as voltage sensitivity. Obviously V is equal to IR, alpha will be equal to I into R. And from here you can see, we know very well the value of alpha. Alpha is equal to NBA by K into I. So this II will get cancelled and you will be remaining by NBA by K. So IS will be equal to NBA by K, isn't it? And now, so what is the use of figure of merit? So once again I am saying that figure of merit which is equal to G. Last play I told no, I is equal to G alpha. G will be equal to I by alpha. This is only known as figure of merit, G. So it determines current per unit twist. So the more the G, the more the value of G, that is the galvanometer constant, the more deflection your needle will show with the less current. So current per unit angle of twist is known as galvanometer constant, and this is only called as figure of merit. I think I have answered the question, Abhishek. So here if you want to write, it will become equal to NBA by K into R. This is about the voltage sensitivity. So I hope it is clear. Let us go to the next page. Okay, a question is there. Current sensitivity of a moving coil galvanometer is 5 division per milliampere and its voltage sensitivity is 20 division per volt. What is the resistance of the galvanometer? We know very well that Vs is equal to Is by R. So here they are asking to find the R, which will be equal to Is by Vs. Now Is is given as how much? 5 by milliampere. So 5 divided by 10 to the power minus 3. And Vs is given as how much? 20. So 5 4s are 20. It will be equal to 10 to the power 3 by 4. So it will be equal to 250. 250 ohms is the correct answer. Simple question. Next. So now we should know how can you convert a galvanometer into either an ammeter or into a voltmeter. So a galvanometer can be converted into an ammeter or into an voltmeter also. So how? Just by connecting a resistance. So what happens if you have a galvanometer like this? And in this galvanometer, if you connect a very small resistance in parallel, it is called a shunt. It becomes ammeter. This whole thing is called as ammeter. Or if in the galvanometer you connect a high resistance in series, this has become a voltmeter. This is a voltmeter conversion. So in voltmeter what we do? We connect a high resistance in series. In voltmeter, in ammeter what we do? We connect a low resistance in parallel. Now why we do that? Why we do that? In voltmeter we want to make the resistance low, isn't it? And in the ammeter you want to measure the current most accurately. So for doing that you want to make the resistance to be low. In this you want to make the resistance very high. That's why you are connecting the resistance in series, a high resistance in series. So if you see the formula, suppose I current is coming inside, Ig goes here, then I minus Ig will come here, isn't it? So here if I is going, same Ig will go in both. So in conversion to ammeter, if I want to write the equation, the voltage will be both, same across both. So I can write Ig into G is equal to I minus Ig into S. So shunt can be found from here. That will be equal to Ig into G by I minus Ig. Same way you can find the R from here. How much R you want to put? Total V is equal to IR, right? So in this case, Ig into G plus R. Ig into G plus R will be equal to V. So R will be equal to V by Ig minus G. So how much shunt you have to add? That will be equal to Ig into G by I minus Ig, and how much R you have to add will be equal to V by Ig minus G. So Kritika is asking, what should we have to do in apparatus to increase the sensitivity of galvanometer? So when we learned about the sensitivity, you can see the parameters on which we can find what requirements are there to increase the sensitivity. So you can increase sensitivity by changing its angle of twist, isn't it? Because sensitivity, if it is current or voltage, that was equal to NBA by K or NBA by KR. So if you want to increase the current sensitivity, you want to increase the number of turns or increase the magnetic field, increase the area of cross section, or reduce the value of torsional constant. Torsional constant we can change by changing the spring itself. So if you increase the number of turns, or if you increase the magnetic field, or if you increase the area of coil, or decrease the torsional constant, you can change the current sensitivity. And to change the voltage sensitivity, you have to even reduce the or change the R value. I hope I could answer you, Kritika. Once again, can I see the comment section once again? So in comment section, some other even doubt was there. That is Vaishali Sharan. Vs is equal to Is by R. Very good. R is equal to, okay. You have told the correct answer. Yeah, that is correct. Fine. So I hope you have understood the conversion of galvanometer. If you want to convert galvanometer into ammeter, shunt of Ig into G by I minus Ig should be added in parallel. If you want to convert galvanometer into voltmeter, V by Ig minus G should be added in series. High resistance in series, low resistance in parallel. So Harshvardhan, sir, can we use phosphor bronze of spring for MCG? Yeah, you can use. They are using that only mostly. Phosphor bronze for making the MCG. So one second, yeah, this we have done. So now we come to the magnetism, right? So now officially I am entering into the fifth chapter. After finishing the magnetic effects of current, that is magnetism and matter, I am entering into the Earth's magnetism. So what is magnetism first? Magnetism is just a phenomenon of attracting the magnetic substance, right? Suppose iron is getting attracted by the magnet, or another magnet is getting attracted by some other magnet. These things comes under the category of magnetism. So there are some properties which I have listed of a bar magnet. So if I have a bar magnet like this, if I have a bar magnet, it will have some properties. Let us see what are the properties of bar magnet. You know very well it has a north pole, it has a south pole, and all these magnetic lines of forces. A freely subtended magnet aligns itself in north-south direction. Yeah, we very well know. If you hang a magnet by a thread, it will automatically align itself into north-south direction. Unlike poles attract, like poles repel, you know very well. Magnetic poles always exist in pairs. Yeah, very, very important point that you cannot separate the pairs. If I break into two, I will get once again one south, north, isn't it? And here it will be south and north. Once again, if I break into small, once again I will have a south, north, and here I will have south, north, like this. So there is no end. You cannot make only one pole. Poles always exist in pair. Magnet can induce magnetism in other magnetic substance. Obviously, if you keep in contact, it will change its dipoles and it will make it to be a magnet. It attracts magnetic substances. So these are the very basic properties of any bar magnet. So going to the next page, current loop as magnetic dipole. Yeah. So how a current loop acts as a magnetic dipole? I just now told you that if you have a current carrying loop like this, current carrying loop. So you know very well that if you are seeing from this side, it is looking like, I mean, here I have made it into clockwise. So if you see from this side it is clockwise. If it is clockwise, then this surface behaves like the south pole. So here we have the south pole. And this side, I'm talking about the back side, I cannot draw on the board. In the back side, if you see, it acts like a anti-clockwise, and there it will be north pole. So what I am trying to say, that this particular loop having some area of loop as A, this particular loop is having north pole on one end and south pole on one end, definitely it will have some magnetic field, isn't it? So any current carrying loop, it acts like a magnetic dipole, and magnetic dipole has a magnetic moment M, and that is equal to I into A. Remember this, magnetic moment, or I should say magnetic dipole moment, is equal to IA, and unit will be equal to Ampere meter square, isn't it? You may have some basic questions based upon this. So if I go into the next page, then you will have bar magnet as an equivalent solenoid. So if you have a solenoid, it acts like a bar magnet. This also is very much known to you, that the resemblance of solenoid is always like a bar magnet. It has a north pole, south pole, same way it will also have north pole and south pole. So let us come to a question. The poles of magnet cannot be separated by breaking into two pieces. Yeah, absolutely correct. The magnetic moment will be reduced to half when a magnet is broken into two pieces. It's obviously magnetic moment will be separated, but magnetic poles cannot be separated. So if you have total magnetic moment as IA, it will become IA by 2, IA by 2. But poles cannot be separated. So obviously A and R are true, and R is the correct explanation of A. Let's go to the next page about Earth's magnetism. Okay, so Earth magnetism, let us know what is the Earth's magnetism. So I think most of you will know that Earth itself behaves like a big magnet, right? So inside the Earth, we believe that there is a magnet. Actually, there is no magnet inside the Earth. How the magnetism is coming inside the Earth? It is coming due to the molten metals which are rotating along with the Earth's rotation. Since the Earth is rotating, along with the rotation of Earth, even the molten metals are rotating. They will have anions and cations. Ions will be there, so charge will be there. If charges are moving, current will be there. If current is in circular path, magnetic field will be there. So we assume that there, due to the movement of some molten materials inside the Earth, we have some magnetic field coming. So here we have the north pole, here we have the south pole of the magnet inside the Earth. Magnet means it is an imaginary magnet. This thing is coming because of the movement of the molten materials inside the Earth. So this point or this line is called as geographical axis, and this line is called as magnetic axis. So this will be called as magnetic north, this will be called as magnetic south, this will be called as geographical north, and this will be called as geographical south. Very basic thing I am telling you. And magnetic axis is tilted from the geographical axis by some 11.3 degrees. Note this, remember this. So if I go to the next page, that is about the elements of Earth's magnetism. Very, very important thing. Elements of Earth's magnetism. So basically we have three elements of Earth's magnetism: angle of dip, declination, and horizontal component of Earth. Let me tell you what is that. So you know very well, if this is the earth, then we have geographical axis and we have magnetic axis. Now if I take a random point on earth, this random point on earth, if I connect with the geographical meridian, this is called as geographical meridian. Geographical meridian. So what is geographical meridian? Geographical meridian is the plane which connects geographical axis with the point. This point can also be connected with this magnetic meridian. See, magnetic axis. This will become as magnetic meridian. So what is magnetic meridian? Magnetic meridian is the plane which connects the magnetic axis with the geographical axis, with the point where we are finding, and geographical meridian is the point connection of the point with the geographical axis. So for the previous question, would not the answer be B? Okay. So I'll come back to you, Abhishek. Let me I have to finish the portion. Time is up. So I'll come back at the end. So I have geographical meridian. I have magnetic meridian. So if you have a geographical meridian like this, and you have magnetic meridian like this, the angle made between the geographical meridian and magnetic meridian, this is called as angle of declination D. Angle of declination is the angle made by the geographical meridian with the magnetic meridian. One more thing, angle of dip is found by the dip needle. Dip needle will move only vertically. It will not move like this. It will move like this, up and down. So if you go to different places of earth, it will dip little bit. And how much it dips, that gives you the angle of dip. So I'll tell you, on the equator, near the equator, angle of dip told as inclination or I is 0 degrees. And at the poles, angle of dip is 90 degrees. That means in the equator, a dip will be like this. Dip needle will be like this. On the pole, dip needle will become like this. It will be perpendicular. So dip needle is 90 degree. That is, dip angle is 90 degree. And one more thing, dip needle is always in the magnetic meridian. So suppose if it is tilted like this in the magnetic meridian, then this, suppose it shows the direction of magnetic field. This is the direction of magnetic field of earth. Then obviously here we will have BH, this angle is called as angle of dip I. So it will be called as, this BH will become equal to BE cos I, and this will become BE sin I. Now horizontal component of the earth's magnetic field, BH is equal to BE cos I. Very important thing, you will have questions based upon this. Angle of declination is the angle between the magnetic meridian and geographical meridian, and angle of dip is the inclination of dip angle with the horizontal component of earth's surface. So by all these things, you can locate any point on the earth. So I hope this is clear. I have gone a little fast, but I am running out of time, very sorry. So this question, I think he asked the last question whether the option will be B or not. So magnetic moment will be reduced to half when a magnet is broken into equal pieces. No, Abhishek, magnetic moment will not be reduced. Only magnetic pole will be same. Magnetic moment will definitely be reduced. Are you getting a point? You are thinking that magnetic moment will not be reduced. Why it will not be reduced? It will be reduced. Only magnetic pole will not be reduced. Every time it will be half pair. But magnetic moment, if it is IA in the first case, break it, it will become IA by 2, IA by 2. Break into 4, IA by 4, IA by 4, IA by 4, IA by 4. So magnetic moments get separated, but magnetic poles don't get separated. I think I answered you, Abhishek. So let us come to the last question. Last question is the angle of dip at a place on the earth. Just now I told what it gives. It gives the direction of earth's magnetic field. So very sorry, ran a little fast at the end because actually I am running out of time, and many of you definitely would be bored by now because we are running for a very long time. And believe me, whatever we are learning, it will be worth it. It's not like simply we are wasting our time. It will have its own importance. So please make sure that if you have not seen this video fully or you have skipped some part, you once again come back and see the videos well. Because videos, whatever we are making, with a lot of dedication I am making. Each and every concept I am trying to cover, each and every kind of question I am trying to cover. I hope you get benefited from this, and that's what we need. So if you have liked this video, please like it, subscribe to our channel. Thank you.